So let me go ahead and start recording again. So for the recording, I was just mentioning how Canvas was bugging out a little bit, and it takes me a little longer to upload these videos. I don't know why Canvas isn't letting me upload the videos as files, and I have to essentially insert the videos into specific pages on Canvas, new Canvas web pages, and then post those to the module section. And for whatever reason, it just takes a lot longer. So I'm sorry if these videos are going to be delayed in the day. I'll try my best to get them uploaded to Canvas as soon as possible. Okay, so the topic for today, we want to continue with parametric equations. And we may want to get into the calculus a little bit, or we are going to get into the calculus a little bit. The main topics with calculus that we have, of course, we want to be able to take derivatives. We want to understand and interpret derivatives of parametric equations. And we want to do natural things that we started with doing calculus of typical functions. Primarily, the first thing we were really concerned with was rates of change and tangent lines. So finding tangent lines to curves, tangent lines to parametric equations. In some sense, it's a little bit better, especially because we've seen functions in Calc 1 that didn't have specific tangent lines, or if they have a vertical tangent line, we can't really describe that vertical tangent line nicely. And in many ways, wherever a function has a vertical tangent line, properly in our Calc 1 sense, we have said that the function is not differentiable at those points. Whereas parametric equations give us a little bit better geometric tools to kind of work around that, where we can still say a curve itself is differentiable, and then we actually have some nicer methods to come up with the equations for the tangent lines, for the specifically vertical tangent lines. So maybe we'll see a little bit of that. But first, let's kind of continue on our discussion from yesterday. So we were taking a look at another parametrization, and I kind of just mentioned this right at the end, where we were looking at parametrizations. I'm going to introduce a little bit new notation. I'm going to actually just introduce some vector notation for you guys. For me, I think it's a little just nicer way of organizing the work. We don't have to get too deep into the theory of vectors and really what a vector is. Just think of it as placeholders. So if I write something like this, cosine t sine t, and put the cosine and sine in some angle brackets, almost like it's coordinates. It really is exactly that. It's kind of like keeping track of the coordinates. So you just want to think of this first coordinate is our x function. So this is x of t, and then this guy is y of t. It's essentially the same as writing it if we had it as, I don't know what you want to call it, like a case notation, where we have x of t equal to cosine t and y of t equal to sine t. So really what we're doing in parametric equations, right? We have two different functions now. We have an individual function for x and an individual function for y, and how these coordinates, these specific coordinates, are changing as time progresses. So we just want methods of organizing that information at the moment, and an ordered pair is a fairly nice way to organize that. And then we can use this notation. So this r with a little arrow over it, it's considered like a vector. So this r vector of t is commonly what we call something like the position vector. So the book will use like a curve C is defined by this, and they might have like C is equal to a set of parametric equations. Think of it equivalent instead of having just C and defining an entire curve by a parametric equations, I'm just replacing C with this notation here by our position vector. So really you can think of that position vector as our curve. And so one thing we wanted to compare, let's call that one R1, is different parametrizations. So we're kind of ended on this notion that, well, parametrizations, they give us a lot more information and sort of more breadth, more different techniques to deal with more exotic curves. But because we're introducing more information, so to speak, right, we're keeping ordered pairs of information. We have two sets of information now to keep track of. There's also some degeneracies that arise in certain senses, right? In a certain sense, in terms of the geometry of the curves we're looking at, we're almost getting too much information sometimes. And so we've got to learn how to understand what extra information we're getting and whether or not we need to use that information. So for most of Calc 2, I don't believe we will use it, but we'll introduce the notion of velocity a little bit, and then you'll solidify that a little bit more in Calc 3. So we had this example of a circle, something like cosine t and sine t for x and y. And I mentioned that, well, what's going to happen if we change it to cosine of 2t and sine of 2t? So again, our x and y. So here we have two seemingly different curves, or at least two different parametrizations, the overall curve and the overall structure that these outline in space. Well, let's take a look at what's going to happen. If we had R1, all of my pens are running out. We came up with a table, something like pi over 4, pi over 2, 3 pi over 4. And let's call these x1 and y1. So this will be our x1. This will be our y1. x2 and y2. So we can just put it all in the same table and graph, or at least try to graph, these two supposedly different curves on the same graph. And let's see, so what do we get? We're starting with cosine. So we're going to start at 1, 0. We're going to go to root 2 over 2. We're going to go to 0, 1. We're going to go to negative root 2, root 2. And then we're going to go to minus 1, 1, or minus 1, 0. And then our x2 and y2, maybe we do want another table for that. Let's come up with a different table, actually. And let's do our graph over here. And of course, we're going to have a circle. And let's see, let's maybe give them color so we can kind of tell the difference. Or here's, how about this? Since they're going to be the same curve, we'll see why they're going to be the same curve. Let's do it in black, and then maybe I'll add some notation in green here. So let's draw our circle that we were drawing yesterday. And since we've got green going with R1, maybe we can kind of label some points. Here's our t equals 0, t equals pi over 4, t equals pi over 2, t equals 3 pi over 4. So we're still going around the same direction. Yesterday we saw an example, well, if I just switch the sine and cosine of the x's and y's, not only am I changing the starting point, where t equals 0 is, but we also change the direction we're going around the curve. So that's going to play an important role in velocity a little bit this semester, and definitely in Calc 3. What's going to happen if we have x2 and y2? I'm actually going to change the t values we evaluated at, because on x2 and y2, now I have a 2 multiplied by the t. And what we're going to see happen is that t, and I even labeled it wrong. Forgive me for that. We want this guy as green. Let's make R2 red. So that'll be our red curve here in red notation. And let's do some calculations. Since I'm multiplying the t by 2, 0 is not a bad one to start with. And we are starting at the same position. Let me see if I can get the equations on the screen there with that. But now instead of pi over 4, let's do pi over 8 and then pi over 4. Because what's going to happen at pi over 8, when I put pi over 8 into cosine of 2t, cosine of 2 times pi over 8 gives me cosine of pi over 4. And so that's going to be my root 2 over 2 for both coordinates. Pi over 4 is where we're actually going to be at 0, 1. And then 3 pi over 8 will be at minus root 2 over 2 and root 2 over 2. So check more of those values if you want, and increment your time values by now pi over 8. So what's happening with this green curve? The green curve, pretty easy to understand that not only are we starting here at t equals 0, but we will go all the way around the circle every 2 pi time intervals. But what's happening with the red curve, hopefully you should kind of get an intuition that if I plotted cosine of t versus cosine of 2t on the same graph, and you remember way back from pre-calc, that this should have half the period. That the time it takes time it takes to complete one period, one cycle, is going to be half as long as just cosine of t. And this is exactly what we're seeing with these parametric curves. So our t equals 0 is here, but here we're at t equals pi over 8. So we're already at this point versus the green curve in half the time. And likewise, we are already going around to, excuse me, the vertical position at pi over 4.
Can you scroll down real quick?
Cool. And then if you kept doing the calculations, you would find that we are back here at the origin every pi units of time. So even though the overall curves are the same, the period or the speed at which we traverse the curve can be different for different parametrizations. And not only that, but we can even get more complicated. Namely, if we do something like so let's call this R3. What's going to happen with this guy? So again, this is just our x, and this is our y. And in terms of understanding parametric curves, you kind of want to think, at least in terms of the shape, when you're seeing these equations, what is the relationship between x and y? We'll try to work with some of these here in a second, because our next goal is to be able to go back and forth from parametric equations to Cartesian equations and back and forth. And so what you should get a sense of is, how am I relating these two functions? What is the overall shape or function of x, and what is the overall shape or function of y, and how are those related? You should kind of get the sense that, well, my x of t is still cosine of something, and my y of t is still sine of something. And more importantly, since those two somethings are the same, we should still have this same shape. It's going to be the same shape as a circle overall in the curve. But what's going to be happening here now with a t squared underneath the arguments of those? We saw in the last example that, well, if I multiply the time by 2, essentially it's like speeding up time. Essentially, we're just kind of making time move twice as fast for the inputs of our x and y functions. And so we are traversing the curve twice as fast. Now what are we doing here? How are we modifying this function of time before we put it into these overall shaping functions for x and y? Well, now we have t squared. And what does t squared do? T squared isn't just a linear time coordinate or a linear function. It starts off slow, so it's actually we're going to traverse a circle, but it's going to start slowly and more slowly than just with cosine t sine t. But then as we understand the graphs of just t versus t squared, we know that t squared is going to increase. So it's going to speed up and continually speed up as time increases. So if you want to graph this, time, x, and y, going to be a little hard to pick your times. You got to be clever with it, understanding that we do need to evaluate sine and cosine. So the first time, rather than something like pi over 4, might be a good idea to do like square root of pi over 2. That'll give us root 2 over 2, our root 2 over 2. What's the next one we want? It's going to be square root of pi over 2. So the 2 is also under square root of that guy. And of course, when we square it and evaluate them, we'll just get our 0 and 1. And so once again, we're going to get a circle that is my Michelangelo circle right there. And so let's take a look at what's going to happen. We start here at t equals 0. We'll be here at t equals square root of pi over 2. How long is it going to take us to get all the way around the circle? The first loop will take us between t equals 0 to t equals square root of 2 pi. Whereas the second loop, we will be back around again, square root of 4 pi, which is, of course, 2 root pi. Now, these numbers are a little hard, but you should take a look at maybe just doing some computations. Our first loop, or our first pass through the circle, it took between t equals 0 to t equals square root of 2 pi, whereas the second loop took between t equals square root of 2 pi to 2 square root of pi. And then you can check that square root of 2 pi It's going to be smaller. Sorry, it's going to be larger than the difference between these two. 2 square root of pi minus square root of 2 pi. In other words, the second time around, that loop is going to be much faster. And if you can check the third loop, what time we're coming back at the third, so square root of 6 pi, what you'll see is that not only are we going around this circle, but we are speeding up. So we're starting off slowly, and then we're increasing quadratically, and then we're going to keep speeding up as we go around this circle more and more as time continues. And we're going to be speeding up specifically because of this function of t squared, which is going to increase our speed of the period of cosine and sine. So we want a way of measuring these things, and we're going to do that with calculus. How do we measure rates of change? If we want to measure what is the rate of change at which we are going around a circle, or what is the rate of change that we are traversing a given curve, that should scream Calc 1 at you, right? Derivatives. So we're going to need a notion of derivatives. So let's get into that in a second. Let's do a few more examples and just practice with these parametric curves, because we haven't seen a whole lot of exotic examples, and there can be a lot of different things. We've only seen like circles and like some lines. So let's practice a little bit and try to come up with techniques, at least things you can try to do to get a better understanding when you have to graph these on your own. So some notation, or actually here, let's call it vocab. Math vocab is important. I don't think we emphasize vocabulary enough in math. Too many people get caught up with trying to do the math too much before they really understand what even the words mean or what we're trying to describe. And I think sometimes, like, if you feel like you're struggling and you feel like you're behind, start with some of the basic vocab. If you don't understand what a derivative is, it's going to be hard to use that derivative in related rates and more complicated type problems. So when we say the word planar curve, this just means a curve in the xy plane. In the typical Cartesian plane. And usually we will describe Cartesian curves, or excuse me, planar curves, by either describing them as a Cartesian equation, sometimes we'll use the words rectilinear. So rectilinear, just think rectangle. And so our x and y grid is a nice rectangular grid, or square grid even in that case. So these are, of course, are typical equations relating y and x. So, of course, y is a function of x, even x is a function of y. And then there are more complicated equations, of course, things like circles, x squared plus y squared equals a constant. And beyond that, of course, we could have y cubed minus natural log of y equals xy minus 3. So those are all in Cartesian equations or rectilinear equations, just equations involving x's and y's. And then, of course, now we have our parametric equations. And so getting used to these parametric equations, best way to do it is to practice graphing examples, and then just as well going back and forth from parametric equations to a Cartesian equation and vice versa. So some of it is actually quite easy. And so our method is for any function, if we have y as a function of x, we can get an easy parametrization by setting x equal to t and y of t equal to f of t. This is kind of the easiest case to start with. All the typical functions that we've been working with, natural log of x, x squared minus 10, e to the x. If we need to come up with a parametrization of that, all we have to do is describe it, and if you want to write it as a vector, make x t, and then your y sine of t. If we have y is equal to e to the x minus 2x squared, and we want to come up with a parametrization, if you want to write it in our other method by listing x and y individually, same information written a little differently, x of t equals t, y of t, e to the t minus 2t squared. And likewise, of course, I didn't explicitly write it, but if we have x as a function of y, and what other function do we want to throw in there? Natural log plus arcsine. Parametric equations we can come up with. Our x, we now have natural log of t plus arcsine of t. And then, of course, our y of t, since it's our independent variable, we can just make it equivalent to the independent variable in parametric equations. That is, we'll just set y equal to time. So that's going to be first easiest method. Everyone caught it with notes here. The second method, here, let's call this method 1. And then our method 2 is going to be harder. We've got to use known geometric identities or things like trig formulas or any other kind of mathematical formula and equations that we know from geometry. As I said, geometry comes up quite a bit to simplify the expression. And I'll kind of put that in quotes, quote unquote, simple parametrization. This is where I know some of you guys are going to hate this because it's non-algorithmic. It's not something that you can just push a button, follow a formula. It's going to be one of these things that, again, a lot of people have questions like, how do I know to do that unless I know what the answer is to begin with? And this is the conundrum of math, is you've got to just study a lot of different examples. We're trying to build these intuition of problem solvings and clever examples and clever tricks and expose you to all of this. And eventually, when you understand these types of things more intrinsically, that's really how you develop your deep mathematical skills, being able to develop an intuition for being able to think through and use all the tools in your tool belt to come up with solutions. That's really what makes a good mathematician, good scientist, good engineer. And so examples of this, and I guess I should say the other reason I put the simple in quotes is, well, we kind of just saw that, well, parametrizations also aren't unique. And so there's going to be a lot of you. I mean, even if as some of the solutions I saw on the last exam with these different power series that people were able to come up with for hyperbolic cosine, different power series, different sequences, as long as they ultimately compute the same power series, are still going to be the same. And it's kind of hard to distinguish which one's more simple, which one's the correct form of a power series if both of them describe the same power series. Kind of similar here in parametric equations. We just seen a lot of different ways of parametrizing a circle. Which one is correct? And that's kind of the conundrum. There's never a specific correct answer. And so when I say a simple parametrization, you do kind of want to make it a nice and concise mathematical expression. But at the same time, if your brain thinks a little bit differently and you come up with a solution that is a valid solution that is different from someone else's valid solution, it doesn't make it wrong. So you'll still get all the points for it. So we've got something like x squared plus y squared equals 1, except our x and y are now scaled by different constants. This is x squared over 9 plus y squared over 25 equals 1. So this is why we start with the circle as a building block. Circle is kind of a good building block because it's a well-known function, or not a function, I guess. It's a well-known curve that we know we can't solve for as an individual function. So let's see what's going to happen when we modify it. A lot of those techniques of trig are going to come out with this. So if we modify this, hopefully you guys have seen this somewhere in pre-calc, I hope, that this is going to look like a circle, but it's going to be stretched. Those individual scaling factors on the corresponding variables are going to stretch those axes, so to speak. And so what we get is an ellipse. So our y squared is going to go, or our y coordinate is going to go to -5 to 5, and our x -3 to 3. Check some of those points. So of course this point up here is 0, 5. X is 0, y is 5. Makes a valid statement. X is 0, y is -5. When we square the negative, still gets a valid statement. Likewise, when x is positive and -3. So we get an ellipse. And what we want to do is come up with a parametric equation for it, or a set of parametric equations. And how do we do that? Well, in terms of thinking back on your bag of tricks and what to look for, our bag of tricks right now consists of, okay, if I know y is a function of x, I can just make one of them t, easy peasy. And the other tricks we kind of know as well, okay, if we have x squared and y squared in our equation, maybe we should look for sines and cosines. And why sines and cosines? Because we know sine squared theta plus cosine squared theta equals 1. And that overall form looks very close to this equation we have. We just have to make sure we make the right substitutions. So if we relook at our equation, and if we notice that the 9 and 25 are, nicely enough, squares of integers, of course, they don't have to be nice squares. This could have been a, 10 on the bottom, but 10 is still square root of 10 squared. So I could have had like square root of 10 under this x. So be mindful Sometimes when the numbers don't work out terribly nicely, if the mathematical operations are still valid, they're still valid, even with the numbers of square roots or crazy fractions. And now we kind of compare these two. Our x squared plus y squared, or sine squared plus cosine squared is 1. We've got our x over 3 quantity squared, quantity x y minus 5 squared equals 1 is our equation. And so it would be nice if we could kind of just substitute here. So just as we were doing with our trig subs and with our u subs, you can kind of write down, well, if I know a sine squared and cosine squared will essentially give us the same format of this equation, give us a valid equation, and it introduces this new parameter of, say, theta. So sometimes our parametrization is not necessarily t. We can use any variable for the parametrization. We often use t because we think of it as traversing the curve as time ticks away. But sometimes we can use theta. In our examples with the circle, you really just want to think of it as, well, if this is my theta, and as theta increases as we're rotating around, what is the corresponding x and y coordinates? How would I parametrize my x and y coordinates corresponding to this angle theta as we wrap around? So this is another thing to look for. This is introducing us a little bit into polar coordinates and polar thinking. That if I have some sort of curve that sort of encircles the origin, maybe we can think of x and y as parametrized by this angle as we rotate around the origin. What is the corresponding x and y value? And just as we saw with circles, there are many different parametrizations. I actually put maybe the sine and cosine a little bit out of order, but it kind of doesn't matter. So there's going to be several parametrizations. So what do we want if we want to use this Pythagorean identity? Well, we can make x over 3 equal to cosine theta, and then y over 5 equal to sine theta. And so what is our parametrization going to be? Our x of theta, I wrote a t, is just 3 cosine theta, and y of theta is 5 sine theta. And so this is our parametrization. Of course, it's one parametrization. If you would have said x over 3 equals sine theta, y over 5 is our cosine theta, you would get something similar. Still an equivalent parametrization, a good, valid parametrization, just looks different. So either of these answers would have been correct. You could even throw in different periods if you really wanted to. They would be correct if you want to even get fancier. Of course, typically when we just want any parameterization, you try to keep it as simple as possible. So check those on your own if you want to plot these as parameterizations. Pick our values of theta like we were doing with the circle. And you'll see that just by scaling these factors, really what are we doing with our x coordinate? If we start with a circle, a unit circle, and now scale the x values by 3, we're just stretching the x bounds by 3, and likewise we're stretching our y bounds by 5. So you'll find that we get a nice ellipse with that. Okay, so our next question now is, well, what if we want to go the other way? And the other way is actually a little bit harder. Coming up with parametrizations from known equations usually isn't too bad, at least with if the known equations we give you are usually known curves, known functions that we've been working with for however many years in your calculus and pre-calculus programs. But now going the other way, it can be tricky. So let's just see a couple of examples. The methods are essentially going to be the same. It's just that sometimes they can get a little trickier in this case, I think. So for example, if we are given Cartesian parametric equations of e to the square root of 3 or square root of t, and y is equal to 3t minus 1. There we go. So of course, again, this is our x of t, and this is just our y of t. And we want to find Cartesian equations. So just like in method 1 and the other way, our method 1 is going to be related, a little bit more involved, and it's simply to look to solve one variable or one equation for t and then substitute. So we have our x is equal to e to the root t, and y. I'm going to drop the argument there. So y is equal to 3t minus 1. We don't need to keep the x of t when it's kind of implied that x is a function of t, just to make it a little easier on our writing and sort of visual way of looking at this, especially because we are solving for t in terms of one of the other variables. Which one you guys want to do? Easy preference? Probably that guy, right? This guy's easiest to solve for t. We can do this one too if we wanted to use natural logs, but we don't have to. It also kind of depends on what the question asks. Like if we are trying to solve y as a function of x versus x as a function of y, sometimes we have to either choose one, or we could choose either of them and then finagle it in the end. So we can see, let's see how to do that. So of course, if we wanted to solve for t here, what are we going to get? We're going to get y plus 1 all over 3 is equal to our t. And then so what do we have to do to find Cartesian equation? Well, I just substitute this guy in for t into the other equation. So we would get x is equal to the exponential of square root of y plus 1 over 3. Let me write that a little better, give myself some space. And that is a valid Cartesian equation. This is x as a function of y. We could try to write it a little more nicely and get any other valid sort of Cartesian equation from it by performing our well-known operations. We do want to be careful about the domain and ranges of y as well. So you want to be careful here. What is our values of t in the original equation? Because we have the square root here, our t can only be from 0 to infinity, or maybe some subdomain of that. But let's keep the maximal domain we can have, square root or 0 to infinity. And what is this domain going to dictate about our x's and y's? namely our x's. What's the domain or the kind of hard to talk about domain and range now. Let's say the set of valid values. Of course, domain and range, our domains usually are set of independent variables, and our range is the set of dependent variables. But now that we have a parametrization, really the only dependent or independent variable was time. And then as soon as we move to a rectilinear equation, it could be either or, depending on what we want to solve for. So really, we were looking for the set of valid values for our x's and y's. So x is going to be between 1 and infinity, right? If we plug in 0 in for x or for t, we will get e to the 0, give us a 1 for x. And as t increases, this is just going to be an increasing function. Square root of t increasing, e to the x square root or increasing. Likewise for y, since we are restricted on 0 to infinity, our y is going to be between -1 and then increasing, so increasing up to infinity. So sometimes you would just want to be careful with that. As the rectilinear equation that we have written, I can plug in -1 for y. That'll give us a valid statement. And of course, it'll give us x equals 1. And then as y becomes bigger, still valid mathematical operations, and we'll be fine with that. If we wanted to come up with other rectilinear equations, especially once we start using natural logs, you want to be careful because, of course, the domain of a natural log is 0 to infinity. Nicely enough, since our x values are from 1 to infinity, we can take a natural log of x, and that's going to be perfectly fine. So if we wanted to come up with other rectilinear equations, we would get natural log of x is square root of y plus 1 over 3. And so another valid Cartesian equation. Now, neither of them are written as a function of the other, but it is an equation relating the variables x and y. And if we wanted to, we could solve for y. So we would square both sides, multiply by 3, and then subtract 1. So here we have y as a function of x. And again, our x interval is 1 to infinity, so we're not going to get any invalid operations there with the natural log. And so here we have y as a function of x. And this would also be the same equation that we would get if we would have solved this guy first. So again, take a natural log of both sides, square it to get natural log of x squared is equal to t, and then plug that in for the t for y. And of course, we get this equation. So in nice enough situations, sometimes it doesn't matter which one you start with, as long as you're able to solve for t. Heads up though, it's not always that nice, right? Sometimes we might have x of t is, if I put a t here, if I made it t e to the square root of t, well, now we can't solve that equation for x or for t in terms of x. But this equation we can solve for t in terms of y. So sometimes there's a definitively clear, easier coordinate to work with, to start with, in terms of coming up with a Cartesian equation in this method. Okay, I want to do one more example, and then we can jump into the calculus. And of course, the second method is kind of the same as the second method going the other direction. It's just we want to look for geometric and trig equations or relationships. So for example, here. So let's say I have a parameterized curve given by x of t is 2 sine t, and y of t is 4 plus cosine t. graphing this actually isn't going to be too bad. It should look very similar to an ellipse because we've got this sine t and cosine t, and then it's just that our y coordinates are shifted up by 4. So the y range is going to be between 3 to 5. X range is going to be between -2 to 2. And it should look like an ellipse just shifted upwards. If we want to find Cartesian equations for that, though, the process becomes a little trickier. So you kind of have to just look at what types of functions you're given and then trying to come up with a relationship, whether it's a geometric trig or other mathematical equation. And specifically, since we're given trig functions within our parametrization, we at least know we have the Pythagorean identity. And so we should look to potentially use that somewhere. And how do we get that out? Well, sometimes you just got to do a little bit of scratch work and play around with it a little bit. So let's write it out. We've got our x of t, or x, is just going to be 2 sine t. And our y is 4 plus cosine t. And there's a couple ways to go about this. We could try to like compute x squared and just see what happens. That'll give us a 4 sine squared t. And that's pretty nice. That sine squared, of course, in the Pythagorean identity. But what's going to happen if we try to compute y squared? We have to square this entire guy out. And while it will give us a cosine squared, it also gives us all these extra terms. So it kind of raises a question of how do we use that? And you could try to use something, maybe even try to substitute a y into that, right? If I write this as, so 16 plus 8, you would have to finagle the constants, either factor them out and then maybe add and subtract something else on there to get it something that looks like a 4 plus cosine of t times some scalars and maybe adding some other scalars to substitute a y into there. The other thing we could try, since we want just a cosine squared for our identity, we can say, well, y minus 4 is equal to cosine. And so y minus 4 squared gives us our cosine squared. And now this is a little bit nicer, right? We see sines and cosines in the parametrization, and since we are able to do some fairly simple algebra here to isolate your sines and cosines, namely, we could solve each of these equations. Now I could solve for at least sine of t, and I could solve this one for cosine t. And if I had solved this one for sine t and then squared it, we would get, of course, x squared over 4 is sine squared of t. And now what do we want? Well, what is the relationship between x and y? I know that this equation is valid and this equation is valid. And of course, the Pythagorean equation is valid. So from our equation of sine squared plus cosine squared, we can make this relationship that x squared over 4 plus y minus 4 squared equals 1. And what we've come up with is now a valid rectilinear equation. One thing to note, and something you might want to be careful with, especially when we're trying to use things like method 1, you might say, well, I can solve for t, can't we? We could divide this by 2 and then say, let's write this out. So just be careful. What if we try something like arcsine of x over 2 is equal to t? What's our problem here? Right, if we're trying this for x is equal to 2 sine t, this runs into another domain issue. I didn't list the domain on the original functions or the original parameterization. So if the domain isn't listed for t, assume it's a typical domain as large as possible, aside from any other invalid points. So in the last example, we saw square root of t, meaning t had to be from 0 to infinity, was the largest t range we could have. In this case, if I didn't specify, we know that t is going to be between minus infinity to infinity. That is our natural domain for sine of t. But what's going to happen here? Well, our x, if t is going to be between minus infinity to infinity, x is going to be between minus 2 to 2. Arcsine is going to spit out what values? We'll call it arcsine of anything. Let's just give another dummy variable. U is, let's say, has restricted output. Not only is the domain of inputs restricted, so the inputs have to be between minus 1 and 1, which we're fine with. The problem is the outputs are going to go from minus pi over 2 to pi over 2. In other words, the output of arcsine would be minus pi over 2 to 2. And so that's going to restrict our t values in that case. So it's not a bad thought, not a bad process, but we are kind of destroying some of the natural information that we started with. So be careful with some of these algebraic manipulations, especially if you're using inverse trig or natural logs like we had to use in the last one. Anytime we are applying mathematical operations, or if we apply a square root, you could potentially be changing the domain or range of outputs that naturally exist within a parameterization. Sometimes you have to, and it's like the only method, but if you can find a way around it, whereas with these operations, here our t is still minus infinity to infinity, and we didn't really mess with that at all. Of course, you might have been able to arrive at something the same way with arcsine of x over 2 when we plug that in for the t, and then you would have had to do a bunch of evaluating trig, evaluated on inverse trig, and you could do the math that way. And then after you work it out, though, I would be careful, because especially if we solved y as a function of x, right? If I was to take this substitution for t as x, we would have ultimately just solved for y as a function of x. And what would have happened? It would have likely only given us half of the curve, like a top half where y was positive. So careful with stuff like that. It can come up. Okay, so let's jump into the calculus. Do you guys want to take a break? Yay, nay? Yeah? All right, so let's take a break for a few minutes. We've got 10, 15 minutes left after the break. That'll give us enough time to introduce some of these concepts of calculus, and then we'll also have all day Monday to practice all of the calculus of parametrizations. And then I think on Tuesday, we'll start in with polar coordinates, And then by Friday, we'll be ready for the midterm, for the final. Okay. So we want to address a little bit of this extra information that we're starting to get with these parametric curves. Of course, we've seen the fact that we can have different parametrizations for the same curve. And moreover, we're starting to see that the way these curves are traversed with different parametrizations give us this notion of a speed that we're traveling along the curve. And anytime we have a notion of a speed or a velocity, we want to consider that as a rate of change of position. So calculus is going to be involved. So calculus of parametric curves, primary things we're going to be looking at are derivatives, which give us a notion of velocity and speed. So when I say velocity and speed, these are two related terms, but they are different. And then, of course, curvature, which is going to be related to acceleration. And I guess if we're going to keep our lists going, what else do we get from velocity and speed? This is all first derivative. And curvature, acceleration, concavity, all comes from our second derivative. And then the other types of calculus things we're going to look for are arc length. So we just learned arc length this semester. It's actually easier to do. I think arc length is far, far easier with parametrizations. The arc length functions and arc length curves we saw in the homework, they're very niche, very specific because of that specific arc length formula. We had a square root of 1 plus f prime of x squared. And so there's only like a very special class of functions where if I take their derivative and square it and then add 1, we can compute a nice square root of it and then integrate. So a lot of those problems had to be cooked up very specifically, but using that formula in general doesn't really work. For parametrizations, we'll have a little bit more breathing room in terms of the types of functions we're able to find arc length for. And then, of course, we want to look at areas. So we'll probably get to arc length and areas on Monday. For now, let's take a look at derivatives and what types of information that gives us. And let's see, do we want to start with an example? Start with a little bit of theory. We've only got about 12 minutes, and then maybe we'll jump into an example and probably finish that example on Monday. So given a parameterization, which I'm going to write as, just again, R of t is an ordered pair of our x parameterization and our y parameterization. What we can do is just compute derivatives component-wise. So when I say components, I mean the individual coordinates. And so we would write this as maybe r prime of t is equal to, well, I'm just computing the derivatives, x prime of t, y prime of t. Or if you want to use Leibniz notation, dx dt and dy dt. So if this guy, we can call it our position curve, or we might call it the position vector. So for now, don't worry too much about the word vector. Think of it just as a vector as an ordered pair of information, an x-coordinate and a y-coordinate. And if you wanted to go into 3 dimensions, you could easily generalize a position vector as x-coordinate, a y-coordinate, and a z-coordinate, and potentially information about how those coordinates are changing over time to create a curve. Then this guy here is going to be called our velocity vector. And so note that it has a direction and a length. So this is the difference between speed and velocity. Speed is just the magnitude, how fast you're moving. Velocity is how fast you're moving, but also encoding the information of which direction you're traveling. So we'll get into that a little bit more as we draw these curves and as we draw these tangent lines. We'll see what we mean by this velocity vector and maybe get a little bit better understanding of what a vector is as well. But it's pretty easy enough that if I have x of t and y of t, when I take their respective derivatives, well, now I've got the derivative of x. So we can really think of this as this is the rate of change of my x coordinate with respect to time. As time ticks, how fast am I moving in the x direction? As time ticks, how fast are we moving in the y direction? The rate of change of y with respect to time. So typically what we want to do, though, is to compute dy dx. If we're just talking about pure curves in space, usually when we want our tangent lines, we want our rate of change. We want our slope of the tangent line so that we can actually create an equation of a line. So how might we compute dy dx? Well, we simply do this with our chain rule. So one thing to note, you can do this and derive this in two different ways. Dy dx is going to be dy dt times dt dx. And then we could take the reciprocal of this. Some people may not be terribly comfortable with that. If you're not incredibly familiar with first order differentials, I've mentioned they behave in very much like typical variables. These dy dx's, these dy's and dx's separately behave pretty much like variables. So multiplying and dividing them is fairly consistent. So you do need to justify why is dt, the rate of change of dt with dx, with respect to dx, 1 divided by dx dt. Of course, the other way we can get to that is simply by taking a look at dy dt and using essentially the same chain rule. Dy dt is going to be dy dx times dx dt. And now this itself is a function we would compute and divide over. So we get essentially the same equation. So in other words, this simply tells us that if we're looking for the rate of change of y relative to the rate of change of x, well, in our parametric curves, we have a list of information. We have the rate of change of x with respect to t and the rate of change of y with respect to t. And since t is the same variable for both of those, if we really want to find the relative rate of change of y with respect to x now, all we got to do is take the quotient of those two rates of change. So hopefully that makes sense. It should feel very natural in terms of comparing our rates of change, our relative rates of change of the two variables, simply by taking the quotient. So let's start an example. Now, one of the things that's happening with parametric curves that isn't happening with functions when we draw these curves is that sometimes parametric curves can cross themselves. Oh, am I lagging? I got a blip earlier just before the break that said my internet was getting some lag spikes. Where did I end? What did you guys hear? What did I leave off?
You had basically just written the last line on the paper. Yeah.
Okay. So I didn't really say much after that. I was kind of just describing how the relative rates of change of x and y, it should feel very natural that if we want to compare the rate of change of y with the rate of change of x, and we have in our velocity vector the information coded of the relative rate of change of x with respect to time and the rate of change of y with respect to time. And if we want to compare the rates of change of y with respect to x, natural thing to do is just take the quotient of those two values, especially since time is going to be the same value. Time is changing at the same rate for both of these variables. So let's take a look at an example. And as I was saying, a problem with parametric curves is that sometimes parametric curves can cross themselves. So here's going to be our example. Our r of t is going to be given by x is t squared and y is t cubed minus 3t. And again, our t is between minus infinity to infinity. So we could try to come up with a closed form expression or a rectilinear or Cartesian expression for this curve. But again, we're going to have to be careful, especially with this t squared and this t cubed. This one's going to be hard to solve for t in terms of y because of the t cubed minus 3t. We could solve this one in terms of x, but we would have to restrict ourselves to certain values of t. Either they're plus or minus, depending on which square root we take. So first part of this question is going to be show that we have two tangent lines at 3, 0. And so this is a phenomenon with parametric curves that sometimes a parametric curve can loop around and cross itself, meaning it's going to hit the same point in space at multiple times. And depending on which time we hit that point, we're going to have a different direction of travel. In other words, giving us a different tangent line, a different velocity vector. So let's see how we would solve this. First part, we are going to show we need to find when we hit that. So we're about out of time, so let's try to do this fairly quickly. We've got 3 is equal to t squared, and then 0 is equal to t cubed minus 3t. So this one we should get t is equal to plus or minus square root of 3. And this one, when we factor it out, we get 3 different times. So which times do we choose? The times have to be consistent for both of the variables. Meaning at time t equals 0, my y-coordinate will be at 0, but the x-coordinate will also be at 0. So at time t equals 0, we're at the point 0, 0, not at 3, 0. So we actually don't need that one. However, we saw that at these common times of square root of 3 and negative square root of 3, my y value is again at 0 and my x value will be at 3. So the two times we want are going to be square root of 3 and negative square root of 3 of when we're crossing this 0.30. And then our next step is to find the tangent lines. So real quick, let's just go ahead and take our derivative. And let's put it in a vector form just to save ourselves some writing. So of course we'll have 2t and then 3t squared minus 3. And what do we want to do with our times? We would want to plug in our times into our velocity vector. Or we could find our dy dx first, find an equation of dy dx potentially now as a function of time, and then plug in those two times into that equation to find the slope we are traveling at corresponding to each time. So we'll see that on Monday, and then we'll jump into the rest of calculus as well.